The noble gases, explained by Logan and Emma Schoenemann. The noble gases are located on the right side of the periodic table. This is shown in the orange box surrounding them. The noble gases are helium, neon, argon, krypton, xenon, and radon. The noble gases are on the right side of the periodic table because the number of valence electrons increases as you move from left to right across the periodic table. Neon, argon, krypton, and xenon were discovered by Sir William Ramsay and Morris William Travers in the late 19th century. The way they did this was by vacuuming air out of a flask. Once they did this, 1/120th of the air was left unreacted. Since such a little amount of the air was left unreacted, they were led to think that there was some gas remaining. They didn't know what this gas was since it didn't react with anything in the surroundings, but they hypothesized about the existence of inert gases or nearly inert gases. Helium was discovered by Pierre Jensen. He studied the sun and was looking through it one day through a spectrometer. By doing this, he observed yellow spectral lines, which had not previously been observed. This led him to further his research and discover helium. The noble gases took longer to be discovered than most of the other elements on the periodic table because they are nearly inert and they don't readily react with things. The reason that they are non-reactive or almost inert is because of their full valence electron shells. This can be shown in the electron dot diagrams in the upper left-hand corner. Notice how helium looks as if it doesn't have a full valence electron shell because it does not have 8 dots around it. But helium is such a small element that its capacity for its outer valence shell is only 2. Since their valence electron shells are full, they don't want to gain or lose electrons, which leads them to not be reactive, because the gain, loss, trade, or sharing of electrons is what causes reactions between elements. It can be shown in the other image in the lower right-hand corner of the screen that the elements of the noble gases also get bigger as they head down the periodic table. They gain more shells, but they always have 8 valence electrons in their shell after helium. The noble gases emit different colors when their electrons gain energy. This energy can be gained through different outlets such as electricity or heat. When an electron gains energy, it jumps up to different energy levels and then falls back down, producing light. The noble gases gain energy, which produces light at different frequencies. This can be seen through a spectrometer and seeing spectral lines of different colors. The noble gases all have the same number of valence electrons except for helium. But this does not mean that their electrons emit light at the same frequency. They emit light at different frequencies, so this causes them to be different colors. As you can see from the table, helium emits a light purple color, while neon emits more of a dark orange. Argon emits a purplish color, while krypton emits a bright white light. Xenon also emits a light blue. Although they emit a single light when given electricity, when you look through a spectrometer at the different gases, they produce different spectral lines. Such as in helium, you can see a yellow spectral line, while in neon you see more of a yellow-orange spectral line, and in argon there are more blues than yellows. In krypton there are mostly blue, yellow, and purple spectral lines, but in xenon, every color spectral line can be seen. The reason the noble gases have varying numbers of spectral lines is because they increase in size and number of valence shells from helium to xenon. And this size increase leads to a greater distance for the excited electrons to fall. This fall determines the color of the spectral lines and therefore the color the eye perceives. This is how the noble gases compare to other elements. The noble gases have 8 valence electrons, while other elements have varying number of valence electrons. The noble gases are highly unreactive because of their 8 valence electrons, while other elements are reactive because they have varying numbers of valence electrons. The noble gases exist as single atoms because they don't bond with themselves or with other elements. Other elements do bond, so they are naturally bonded to other elements, or themselves. The noble gases have high ionization energies because they do not want their electrons to be taken away from them since their valence shell is already full. Other elements have varying ionization energies because they have varying numbers of electrons. A major use of the noble gases is used in industry, such as oxygen tanks or arc welding. Oxygen tanks contain mixtures of oxygen and helium, which is called a heliox mixture. Helium is added to oxygen tanks because helium is a small atom and at high pressures it is unlikely to explode because it is a very unreactive gas. Helium is also less likely to expand in the bloodstream when a diver reaches a lower pressure by returning to the surface. Arc welding is the fusion of 2 or more metals, and it is done by extreme heat and extreme pressures. When this is happening, the metal does not need to be contaminated, destroyed, or even weakened, so a shielding gas is normally used. Argon is used as a shielding gas most of the time because it is so unreactive and it is one of the largest noble gases, and that gives it more space to shield. Noble gases are used in many different types of lighting. As you can see in the open sign in the top left-hand corner, there are many noble gases present. The orange open word is most likely neon because it glows a bright orange. The blue surrounding it is most likely argon or xenon because of the blue color. Noble gases are also used in the flash mechanism in a camera. It's usually krypton because krypton emits a bright white light. Greenhouse lighting is another area in which noble gases are used, as can be seen in the lower right-hand corner picture. Radon is a noble gas and is nearly inert like all of the other noble gases, but it is not usually included in discussions of the noble gases because it's harmful to the human body. This makes it not very good for use in industry, lighting, or any other applications of the normal noble gases. This should be further studied in the future since they are extremely useful in industrial and lighting settings due to their state of non-reaction that allows them to be used safely.